All right, so we need to go through our section 2 notes for chapter 8 in chemistry. We're going to define and give general equations for a bunch of different kinds of reactions. We got synthesis, decomp, single displacement, double displacement. There's even combustion reactions to add in. Right? We need to learn how to classify each type of reaction. And we also need to predict products of simple reactions given the reactants. So I'm going to break this video in half. We're going to start out by doing the synthesis and the decomp reactions, and then we'll do the other ones tomorrow. Right? So make sure you have some notes printed out, or you're carefully taking notes on your own. Make sure you write down a lot of examples because you're going to use these to compare with later. And make sure that they're accurate as well, because then you can use them to compare and model off of to come up with your own products. So synthesis reaction comes first, right? Sometimes it's called a composition reaction. It's when you have two or more substances that combine to make a new compound, right? The general equation is just generic. It says A plus X gives you AX, a compound with A and X in it, right? The way that you know that something's synthesis, if you want to identify it as a synthesis reaction, is you're always going to be able to see that there's just one product. If I show you a reaction that only has one product, it's definitely a synthesis reaction, right? Otherwise, there are a lot of different kinds of synthesis reactions for us to go through, right? So we'll just do each thing one at a time and add examples and write them in accurately, balance them, everything else, right? Formation of oxides and sulfides, right? Maybe my first example could be magnesium, the element magnesium, again, metal. If I took a piece of magnesium and I burned it, so I'm going to react it with oxygen. If I'm going to do this, it might take a little bit of heat to get that started, but once it gets going, right, I'm going to form this product that has magnesium and oxygen in it. Right, I'm going to make a magnesium oxide. Right, remember, magnesium and oxygen both have two charges, +2, -2. So it balances out 1 to 1. And you have to remember to do that. You have to be able to make that product when it's all said and done. So make sure you remember all your ions and all the charges. But this magnesium and oxygen combine to form this magnesium oxide. But that magnesium oxide only has one oxygen in it. So I have to balance this appropriately. Right? So now I have two oxygens on both sides. Now I have two magnesiums on both sides. Do not write a product and assume that it's going to be MgO2 over here. Just because I had an OT over here doesn't mean that there's going to be two oxides in a magnesium oxide. Do not just make simple assumptions like that. You know how to make formulas accurately, appropriately. Make sure you do it correctly. And so this is not what you're supposed to have. You should not even write that in your notes because it would just confuse you probably. But magnesium oxide, as long as you can make that formula and balance appropriately, pretty easy, right? Take the two separate elements and put them together. But again, notice that I put a magnesium here and I only have one, whereas the oxygen, there's a 2, right? We talked about that before. That's just because that's our general rule, right? For hydrogen, nitrogen, oxygen, any halogen, it's always a 2. It's always diatomic when it's in a formula, in an equation. So you just have to understand when to use those numbers, when not to use those numbers, right? Some of these things you're expected to know, right? And you got to get comfortable with it and not just assume that something's going to happen that doesn't happen. So that's one example. I could also have, any other metal, and let's say maybe I have a barium, and this time I have a sulfur that I'm reacting it with, right? And sulfur might look a little bit different. This is not something I'd expect you to know, but if I gave it to you this way, you've got to deal with it, right? This sulfur could be in this octet, right? But if barium and sulfur reacted together, I'd end up with a barium sulfide. Barium's in group 2, so it also has a +2, just like the magnesium does. Sulfide's in group 6, so it has a -2, just like the oxide does. So I'm not going to put an 8 there. It's 1-to-1. But I definitely get an 8 in front so that there's 8 sulfurs on both sides. And then I definitely need 8 bariums over here. So balance these things appropriately. Come up with your products. Those are a couple examples. Right? Another example could be, I'll just put it up above here. You can fit it wherever you can. Carbon. Right? You don't have to have metals reacting with these things. Carbon could react with oxygen to make carbon dioxide. This time the 2 does end up in there, but that's because carbon dioxide happens to have 2 oxygens in it, right? So I could make that, but technically I might also make a carbon monoxide product. Depends on how much oxygen is available. But again, some things I expect you to know, other things, right, I'd have to tell you more information. I would assume you'd make a carbon dioxide if I gave you carbon and oxygen, and then go from there. So all you do is take those 2 elements and put them together to make a stable compound. We know carbon dioxide is stable. You've heard of it before, right? Magnesium oxide, the formula is 1-to-1. So is the barium sulfide, right? But if I did a sodium oxide, sodium and oxygen, I'd get a different formula, right? So you just do what you have to do. Formation of metal halides, right? Speaking of sodium, let's use that for this example. Sodium could react with any halogen, maybe chlorine. Remember, halogens are all diatomic just like oxygen. So I have to put that little 2 there. Otherwise, to react these 2 things, right, you make a pretty obvious product. You make salt, sodium chloride. Again, that's a 1-to-1, +1, -1. So I don't just put a 2 there because I feel like putting a 2 there. I need to balance the 2 chlorines on both sides. And therefore, I need to make sure that there's 2 sodiums on both sides. But otherwise, you predict the product and you balance. Should be pretty easy. Put those 2 elements together. If it was a calcium, and let's say bromine this time, another halogen, that's why I'm going to put a little 2 next to it. It should be diatomic, that bromine. This time, when I put those 2 things together, because calcium has a +2 charge, and bromide has a -1 charge, I am going to need 2 bromines to go with the calcium. So this one is balanced all the way across. 1 calcium on both sides, 2 bromines on both sides. So again, don't assume anything. Make sure you make that final product to that formula appropriately, because it's a 1-to-1 sodium chloride. It's a 1-to-2 calcium bromide. So it depends on what elements I'm putting together. But you can come up with products you can balance appropriately. All right, so reactions involving oxides. If I have a metal oxide already because I reacted that metal with oxygen. So let's say I have a calcium oxide, right? That calcium oxide can then react with water to make a metal hydroxide. So my product here is going to be a calcium, because that's my only metal, hydroxide. Again, you have to make accurate formulas that balance appropriately. Hydroxide has a -1 charge. The calcium has a +2. So I technically need to write it this way, my formula. So I have a calcium 2 hydroxides in that calcium hydroxide. And then I look to see if I need to do anything to balance. But really, I have 1 calcium on both sides. I have 1, 2 oxygens on both sides. And I have 1, 2 hydrogens on both sides. It's a little jumbled up, but everything's already balanced. This is just 1 to 1, right? 1 to 1 to 1, excuse me. So calcium hydroxide is formed this way, possibly. Right? Whereas I could start out with, let's say, a potassium oxide, react that with water. This would also make a hydroxide. This time it's potassium hydroxide, and potassium has +1, hydroxide has a -1. So I have to write that formula appropriately. This time I don't need the parentheses, I don't need the 2. But I do need 2 hydroxides to get this to balance. But I also needed 2 potassiums because of what's going on over here. So 2 potassiums, again, I have 2 oxygens on both sides. 1, 2, they're both together in the same compound over here. And then I have 2 hydrogens on both sides. So do what you gotta do to balance these things, right? But make appropriate formulas as well. That product that you predict, you have to make sure you balance that correctly, or else you can't do it right in the long run. It won't balance overall unless all your formulas are correct. That's the way it works generally. Okay, so then non-metal oxides also react with water to make oxyacids. So we'll start out with maybe this example. This is a non-metal oxide. This is a sulfur dioxide, right? Sulfur is a non-metal, whereas calcium before was a metal, and so is potassium, so they're different reactions. If you see a non-metal oxide and you react that with water, these are actually pretty simple. You just take all those pieces and put them together. You do it logically, right? The hydrogens are going to be out front because it's going to be an acid, and hydrogen's always out front in an acid. Then I'm going to put my sulfur, and then since I actually have 1, 2, 3 oxygens, this turns into a sulfite over here, right? Which again, I don't actually need parentheses in this case, but just to visualize, there's my sulfite. That was a sulfur and 3 oxygens, right? Sulfite has a -2 charge, so it should take 2 hydrogen ions to balance that out, right? So this whole thing is balanced. It's good to go. All I had to do is take the same pieces, jumble them up, make a product. So that's my oxyacid in this case. And that oxyacid is actually formed when sulfur in fuels are burned, right? When you burn sulfur in a fuel in gas, it turns into sulfur dioxide, right? Then that sulfur dioxide in the air combines with water in a cloud to make this sulfurous acid over here. That sulfurous acid, and this is extra, we don't need this for this chapter necessarily, can react with more oxygen in the air to make sulfuric acid, right? So that there's acid rain falling down, right? So pollution can cause these byproducts to be formed, right? Otherwise, another common one that you should be able to do, carbon dioxide, also a non-metal oxide, it also reacts with water to make an acid. And this oxyacid, again, I just take the 2 hydrogens, the carbon, and then again, there's 3 oxygens. You should see my carbonate in there. Right, but this is a dihydrogen carbonate. This is a carbonic acid. That carbonic acid is in your blood as you speak, as we speak. Right? It's actually important that that acid is in your blood because it provides a buffer system. It helps prevent the change of hydrogen ion concentration, the change of pH in your blood because of other things that are floating around in your blood. So it's actually really important that you have some carbon dioxide in your blood. Not too much and not too little either. There's a Goldilocks amount that is perfect. So when you hyperventilate and hypoventilate, that actually affects the pH of your blood, changes how reactions work in your body. There's a reason why you pass out when you're doing something like that. Otherwise, next reaction, non-metal oxides and, metal oxides and non-metal oxides. When they react, they make salts. So for our example there, we could start out with, okay, let's do that calcium oxide again, and we'll react it with that sulfur dioxide. Again, all you have to do is make a salt. That salt should have two ions, a positive and a negative, right? Start with your metal, calcium, and then the other things combine to make something we should recognize. Again, that's a sulfite ion. This is calcium sulfite that was formed. Right? Sometimes we're confused by this word salt. Remember, that doesn't just mean sodium chloride. It means any ionic compound that could be a result of an acid-base reaction. But calcium sulfate, or sulfite, my product here. Otherwise, I could react, say, like a sodium oxide and a carbon dioxide, and then I'd make sodium carbonate, right? Excuse me, I wrote my sodium oxide incorrectly over here. Trying to figure out what was wrong. Again, if you don't write these formulas correctly, things don't balance very well. I'm supposed to actually have two sodiums on both sides in those formulas, because sodium and oxide, that's not a 1-to-1. Sodium's a +1, oxide's a -2. And then on the right, sodium's a +1 still, carbonate's a -2. So you have to have two sodiums in each compound to make it balance. Otherwise, that's how you make salts, metal oxides and non-metal oxides. Right, up next are our decomposition reactions. Now, understand, I would reiterate, I'm throwing a lot of stuff at you really fast. Just make sure you're writing down these examples and you have good, clear examples, because all you're going to need to do is look back and forth from your notes to your work and just model, right? You don't have to have all this memorized. You're going to use your notes, and you're going to be able to come up with answers, come up with possible products. So, I know I'm going fast, but you'll be all right. Decomposition reactions, though. This is where you have a single compound that reacts to make simpler substances. So if I started out with AX, it could decompose into A and X separately, right? The way that you can recognize a decomp reaction is because there's always going to be now one reactant. Instead of one product for a synthesis, there's one reactant in that reaction. So that's how you know it's a decomposition reaction. Otherwise, all of these decomp reactions are essentially the reverse of our synthesis reactions. Right? All you're doing is taking a compound, right? So we're going to start out with a pretty simple compound that you know of, right? Water, and we're going to decompose it into its parts, into its elemental part. Now this specific example is technically electrolysis, because you actually need some battery to do this, some electricity to do this. Oops. Electricity. I could spell, that help. If I have an electric current, if I put a battery in water, I can actually get it to decompose into its elemental form. But again, hydrogen and oxygen are supposed to be diatomic when I write them in an equation all by themselves. So make sure you do that. Right? But otherwise, in order to balance this, I might need two waters over here. And that means I'm going to make two diatomic hydrogen molecules as a result. Right? The other important thing that we should see here is we can do this reaction as a demo, and you can tell that something's happening because that liquid water, right, over here, these two things are both gases, both of these products. So you're going to be able to see bubbles coming up out of that solution. That's how you know that this reaction is occurring. again, I don't always show the states. I only show the states when it's necessary because that actually tells me what kind of, that reaction's occurring. Right? I know that this happens because I can see bubbles on the electrodes of that battery when I drop that 9-volt battery into a glass of water. That's all you'd have to do. You can do that at home pretty easily. It does ruin your battery. Otherwise, it's not that dangerous, so you could do it if you wanted to. But pretty simple reaction, right? And it's a decomp because you took a compound and broke it down into its parts, its elemental parts. So again, another example, and this would not be an electrolysis reaction example. It doesn't take electricity to do this one. But in order to decompose this mercury oxide, this is a mercury 2 oxide. Remember, it's mercuric because I see a 1, so it's got to be the 2. But I will need something here. I'm going to need a little bit of heat. But when I heat up that mercury oxide, I'm going to make mercury and oxygen separate from each other. In this case, state-wise, my reactant was a solid, but then I'm going to have a liquid mercury. Assume you know that mercury is kind of strange. It is a liquid at room temperature. And then that oxygen would be a gas. But I'm not going to use an up arrow this time because I'm not going to see bubbles here. That gas is just going to be produced and released into the atmosphere. I'm not really going to see bubbles in that mercury liquid. But in that water example before, you definitely see bubbles. So again, states are important sometimes. I also need to balance appropriately. Again, I need 2 oxygens on both sides, so I might need a 2 over here, but then I also need 2 mercuries on the right. So I can decompose, again, mercuric oxide to make mercury and oxygen. Decomposition of metal carbonates. Right? In these examples, again, if you remember, all of these reactions are supposed to be kind of reverse of our synthesis. So if I decompose this, right, if I apply a little bit of heat, because again, most of these decomposition reactions require some kind of catalyst, some push to make it happen, because the synthesis reactions were the ones that were spontaneous, that would happen normally in regular conditions. The decomp you have to force to happen. So just kind of depends. Sometimes there's something over that arrow, sometimes there isn't. Remember this delta that I put over the arrow means that I heat this substance. So I'm going to heat that calcium carbonate, and it's going to turn into a metal oxide and a non-metal oxide. I'm just going to split it up into its parts. But actually, what you should be seeing here is, oh, we made a salt on this last slide, right? Yeah, it might have been a sodium carbonate, but if I was to reverse this reaction, that's what we're talking about right now. So I break it up into its parts. That sodium carbonate would break up into sodium oxide and carbon dioxide, but only if I heated it. Right? Otherwise, sodium oxide and carbon dioxide tend to combine to form that sodium carbonate on the right. So I'm just talking about the reverse reaction of what we've already done. It's not actually new. So be able to recognize that as we go. Right? Again, I might need states, I might not. Right? This is actually a solid. This is also a solid, and this would be a gas. Right? It just go into the atmosphere in this case. But again, the atmosphere contains carbon dioxide that could react with that calcium oxide all over again to remake your carbonate product. So all of these reactions are reversible. Decomp of metal hydroxides. Again, we actually made some metal hydroxides before. So if I started out with calcium hydroxide, excuse me, I forgot to finish my parentheses there, and I heated that up, I I could decompose this to make simpler products. Now again, if I look backwards, I made a calcium hydroxide on this slide over here. So I'm just talking about the reverse of this reaction. If I heated this, guess what products I make? So on my new slide, I'm going to make calcium oxide, excuse me, pen's being goofy, and water. That's what this splits up to make. So again, same reaction, just the reverse. Again, this is probably a solid. This might be a solid. This actually is probably a gas because of the heat, but it could be a liquid. It depends on how hot you got that. So sometimes those states matter, sometimes they don't. But it's already balanced. There's the same number of everything on both sides. The decomp of a metal chlorate. This is a new one, so you have to learn this one, right? Because we talked about a lot of different ions. We didn't necessarily talk about this chlorate every time. I didn't make you memorize it, so now you just have to recognize it and follow with the example. It's pretty simple. If I heated up this potassium chlorate, I'm going to end up making certain products, and it's actually really easy to do. Just take your oxygen out of that compound. If I removed all the oxygen, the only thing left would be this KCl, right? Potassium chloride. But then oxygen is going to be removed, and oxygen is always diatomic. So I have to make sure that this balances appropriately. Since chlorate has 3 oxygens and diatomic oxygen has 2, I'm going to use my least common multiples to get that to work. But then I'm also going to need a 2 here to finish balancing that. Again, depends on the context, but yeah, this is a solid, this is a gas. That may or may not have mattered to us right now. But all you do is remove the oxygen, you end up with 2 products. One you can already see, right? It was a potassium chloride over here, 1-to-1 already, so it stays 1-to-1. And then oxygen is your other byproduct. This can look different if I had a group 2 metal involved. So let's say barium, which would have a +2 charge. Because then I'd need 2 of these chlorides to have a -1 charge. I know we didn't memorize that one, but that's the way it is. I would never ask you to make that, but if I gave it to you on a test, you could deal with it. If I break this up into its parts, I do the same thing, right? I make a barium chloride. I just remove the oxygen. And actually, conveniently, that 2 still applies, right? I have 2 chlorines here, right? I still have 2 chlorines over here. I just kind of slide the 2 over. It works out kind of nicely in this case. But then you also remove your oxygen. And again, same thing as before. I might have to balance this appropriately. But I already have 6 oxygens on the left, because there's the 2 outside of parentheses, which means that I'm going to double this. There were already 3. There's 3 more. There's 6 total. So I'm only going to need 3 oxygens over here, and this whole thing's balanced. Right? But just model off of these examples, you should be able to do fine. Decomp of acids. Again, we talked about this carbonic acid that's in your blood. You don't want too much of that in your blood. As more and more carbon dioxide is dissolved in your blood, that concentration will get bigger and bigger and bigger. But it turns out, when your blood gets to your lungs, where there's a relatively low pressure of carbon dioxide in your lungs, that acid will decompose into its parts. And again, I made it from carbon dioxide and water. So it's going to split up into carbon dioxide and water. Carbon dioxide, in this case, states are going to matter because this was aqueous over here. It was dissolved in your blood. But that carbon dioxide's a gas. It's going to bubble out. It's going to go into your lungs, and then you're going to breathe it out. Right? Whereas the water just stays in your blood. It'll still be a liquid. So this reaction is kind of important for you. But again, it's just the reverse of what we talked about before. Because when I made that carbonic acid over here, I made it from carbon dioxide and water. So if I'm going to decompose it, it's going to turn back into carbon dioxide and water. So all of our reactions have reverse reactions. And that's essentially how you connect those synthesis and decomp reactions together. So don't think of them as separate things necessarily. Recognize that they're similar to each other. That makes your life way, way easier. So as long as you have good examples for all of these, we should be good for now. We'll cover the other kinds of reactions later.